All right, so we're going to be going over what similar polygons are. Similar figures have the same shape but not the same size, but they are proportional. And you will use this symbol. Note that that symbol is very similar to the congruence symbol, right? Equal sign with that little wavy thing. It's the wavy thing, but they're not actually equal. You get rid of the equal part, and you've got similar, okay? All of the angles match, and the sides are proportional. So look at what we got here, okay? You can use proportions and ratios to decide whether the polygons are similar and to find any unknown lengths. Polygons are similar if their corresponding angles are congruent, because remember, if you change the size of a quadrilateral, it's not going to affect that there's still 360 degrees, for example. And if the lengths are proportional, okay, this length divided by this length will be the same as this length divided by that length. You get the same number if you take that length divided by that length and this length divided by this length. Okay, you can write a similarity statement which shows the vertices in order. A, B, C, D. A, B, C, D corresponds with G, H, I, J. G, H, I, J. You can see the marks there making that true. So then the first letter and the first letter line up. Those angles are congruent. Angle A is congruent to angle G, etc. And if you do the sides, the first two letters, A, B, that side is going to correspond to side GH, the first two letters. So AB to GH is equal to BC, the middle two letters, to HI, the middle two letters, etc. Don't forget that when you get to the end, you do DA. There's also a side there, DA or AD. But if you go AD, you want to go GJ, AD to GJ, right? The matching vertices in the right position. Okay, and you can write that as an extended proportion. Also, the scale factor is going to be what you get when if you have similar figures, what you get when you divide one side by the other corresponding side. 15 divided by 6, that simplifies down, dividing by 3 to 5 to 2, right? And all of these do as well. Okay, 5 to 2. Yep, so those are the big ideas for how you look at a congruence, or a similarity statement rather, and how you line up the vertices and name all the angles that are congruent and the corresponding side proportions. So then, if this is the similarity statement, triangle MNP is similar to triangle SRT, MNP, SRT. What are the pairs of congruent angles? Well, you can use the similarity statement, and in fact, that's what this says, right? You can use the similarity statement to write those ratios, okay? The order of the sides, like MN, will correspond to SR, the first two letters, etc. So that's a ratio, okay? What are the proportions there? Well, MN over SR is equal to NP over RT is equal to MP over ST. Yep. Try the Scott problem, see how you do. Okay, so are these polygons similar? If they are, write a similarity statement and give the scale factor. Now, you can identify all of those congruent angles, but when you compare the ratios, by the way, this isn't necessarily a similarity statement. You don't know that J lines up with T, etc. You've got to check it out with the marks here, okay? If you have J, K, L, M like that, and they have T, U, V, W. Yeah, they do line up like that, okay? Just happens to be that they do. But anytime it's not written with that single wave similarity thing, that symbol, then you don't want to assume that those are all vertices in the correct position, because only a similarity statement will show it in the correct position. This is just naming the two figures, okay? But if you line them all up and then you calculate the ratios, you see that this is a 2 to 1, this is a 12 to 7, this is a 3 to 2, and this is a 1 to 1. That's a big clue. If you see any of them have something very obvious like a 1 to 1 ratio and the rest of them don't, you know that it's not similar, okay? Now you can see that in problem 2, this is the first part of problem 2. There's another example in just a second here. So in this one, are the polygons similar? If they are right of similarity statement, this is not a similarity statement. It's just naming the two triangles and give the scale factor. So if we have triangle ABC, let's notice that A to B to C goes from the 2 angle mark to the 3 angle mark to the 1 angle mark. So that's the 2 angle mark to the 3 angle mark to the 1 angle mark, D, E, F. So this is not written in the correct order. So we could say, let's write it there as triangle DEF, just to keep in mind that then this one that I just wrote and this one do have the vertices lined up, okay? Now let's take their scale factor. So what do we want to do? We say, okay, what about the first two letters, AB and EF? AB and EF is 12 over 20, right, etc. And you want to go around and you want to check each one in turn. So let's see what happens when they do that. And when they set those ratios up, AB is to DE, you get 4 over 5 simplified, okay? BC is to FD, BC is to EF, 4 over 5. AC is to DF, 4 over 5. So yes, you can write that similarity statement, a triangle ABC similar to triangle DEF, lining up those correct vertices, and the scale factor is 4 to 5. So now you try it with your got it problems here. So problem number 3 here, they give you the similarity statement and then they say, what is the value of x? We know that they're similar, okay? So what you really want to do here is you want to pick a pair of sides that you know the ratio of, okay? DE, last letter to first letter, right, is to DA, DE is to DA, 6 is to 9, okay? You can think of it like that. Now, can we rely on the diagram alone for proportion to match the proportions? No, we need to use the similarity statement just to be sure that we've got the corresponding sides in order. Okay, so we can do that by, again, saying DE, last letter to first letter on this one, corresponds with D to A, last letter, first letter on that one, this to this, so 6 to 9. And you can then set that up equal to x to 7.5, for example. Okay, the side on the small one, FG, compared to BC, that matching corresponding side. Okay, and what do you get when you set it up like that? You get an x value of 5. This is 5. Okay, try this got it problem. Okay, now this one's interesting. It's kind of tricky. Your design class is making a rectangular poster for a rally. They've got a design written out on a 6x10 piece of paper, 6 inches high and 10 inches wide. And then the space that you're going to be putting this large poster that you're going to make is 4 feet high by 8 feet wide. Okay, what are the dimensions of the largest poster that will fit in the space? So we want to compare this height to this height and see how many times this goes into this, and then this height by this height to see how many times this goes into this. And we're going to be limited by whatever is the smaller number. Okay, you can't solve it until you know which dimension fills the space first. So we say, which one would you fill first? So we're going to convert these to inches and say, okay, if this big one was 48 inches and we divide it into groups of 6 inches, then blowing it up 8 times, we would get that side, which is 6 inches high, 8 times bigger, 48 inches, which is that height. Okay. The width, though, the width is 10 inches, and for an 8-foot space, for 8 feet wide, that's 96 inches. You could get that 10-inch wide thing. If you blew it up 9.6 times, you would be able to fill up the width. But if you blew it up 9.6 times, it would stick over the height because the height can only fit 8 times. So that's the limit that you hit. Okay, the biggest you can blow up is 8 times because if you blew it up to the 9.6, it would be too high. It can only fit 8. So that's what you're limited to. So the design can be enlarged at most 8 times. And then so we say take each one of these times 8 and see what the measurements are. Okay, 6 inches times 8. Or here what they're saying is 6 is to 48. We know it's going to fill the 48. Is 10 is to what? Okay. And we get 80. You can also see that if you multiplied 6 times 8 to get the 48, you'd have to do 10 times 8, and you would get the 80 for that measurement. Okay? Try this got it problem. So we're going to talk here for a minute about scale drawings. Scale drawings, in scale drawings, all the lengths are proportional to their corresponding actual lengths, and then you have a scale, which is the code, which is the ratio that compares each length in the scale drawing to the actual length on the life-size figure or whatever. Okay, and you can see down here on the bottom, we've got for this Golden Gate Bridge, we've got a scale of 1 centimeter in the drawing. Okay, and it can be anything. It could be 1 centimeter to 50 kilometers. It could be 1 inch to 100 miles, 1 inch to 10 feet. And it says, why do we have different units from here to here, from like here to here, or from here to here? Because if you had the same units, we would have these huge, enormous numbers. And we don't need the same units. You'll see what we'll do. We'll say if 1 centimeter is equal to 50 kilometers, then 7 centimeters is equal to X kilometers, and we can calculate for that. But we're still going centimeters to kilometers. Okay. So let's take a look at this. Okay. The diagram that we're looking at here below shows a scale drawing of the Golden Gate Bridge in San Francisco. The difference between the two towers is the main span. What is this length right here? Okay, now this is, I put this in here as a note for you for later, for your problem, but they're saying that this main span, if you actually measured it, would be 6.4 centimeters. So we'll put S to be the actual length of the span that we're looking for. We can say if 1 centimeter is equal to 200 meters, then 6.4 centimeters is equal to how many meters? And when you do the cross multiplication, you find that it is 1,280 meters, the actual span of the bridge. Yeah? Okay. If you have 1 for every 200, 1 centimeter for every 200 meters, 6.4 centimeters will be how many meters? That's how you set it up, and you solve the proportion. So here's your got it problem. Okay, see how you do with it. And by the way, actually let me undo this and let me just slide this up. Okay, so that you can see it up here, because we have 8.8 centimeters is that height of the towers above the roadway. Okay, so you can calculate that. Okay, so you can take this set of lesson check problems and write your answers down and see how you do when you restart the video with the answers. Yep, good luck.